Okay. So I just started to talk about double integrals on Monday, and we'll just continue with that for the rest of the week. First with rectangles, and then with more general regions. So I can illustrate the whole process with, I did one example last time, but here's another. So this goes to what double integrals are used for. This is a single integral is area under a curve. A double integral gives you volume under a surface. So you see everything moves up by one dimension. So compute the volume of the solid bounded by these surfaces, x equals 1, x equals 4. So these are planes that define the bounding x values. And then you have y equals 0, y equals 2. So these are also planes. So the four planes together confine you to basically a box in three-dimensional space. But then you also have boundaries in z. Z equals 0. And then this last boundary is where the integrand comes from. X plus y plus z is equal to 8. So you basically have 6 planes, 1, 2, 3, 4, and then at bottom z equals 0 is number 5, and then you have this other plane, x plus y plus z equals 8, a tilted plane, that's number 6. So those 6 planes make this region. So if I were to try to draw this, and I'll be making a lot of these drawings. It's actually a good idea to visualize what you're trying to work with for your multiple integral in two ways. So free space view that I'm going to do now. So I'll mark these boundaries. So here I have x equals 1, and then further down x equals 4. Now, if you were just in the xy plane, these would be lines. But we're in three-dimensional space, so these describe planes because they're going infinitely up and down with both of these. And then you have y equals 0. That's just the x-axis. And then y equals 2 up here. So if you take all four of these boundaries into account, what you get just in the xy plane is a rectangle. So this is your domain of integration, which I'll call R. So from that region, we're going to get our limits of integration. Now, the xy plane is also z equals 0, so that's the base of our solid. Now, above this rectangle in the xy plane, you have this top that's defined by the plane, x plus y plus z is equal to 8. So what I've drawn here is what we're going to find the volume of. Now, so this is one way to visualize. Now, it's also good to visualize what's happening if you only consider what's happening in x and y. So basically, I'm just taking a two-dimensional slice of this three-dimensional space. So x is between 1 and 4, and then y is between 0 and 2. Because having this view helps you see what your limits of integration are going to be. And this will be very important as we get to more difficult examples. Yes?
Where is z equals 0? Is it parallel to the x or the y axis?
Z equals 0 is the xy plane.
Oh, okay.
Yeah. Yes, wasn't sure. Well, okay. I'll label it down here. Although we're kind of lacking perspective in 3D anyway. Okay. So with integrals, single integrals, so from Cal 2, when you're computing area under a curve, you always had this implicit bottom boundary of y equals 0, the x-axis. It's similar here where you have this implicit boundary of z equals 0, which represents the entire xy plane. Okay, so here again is the same rectangle R that I drew over there. So just as in single integrals you had an interval over which you were integrating, here we have a two-dimensional region, in this case a rectangle, over which we're integrating. Now, with single integrals, you would integrate this function y equals f of x. Here we're going to integrate some function z equals a function of x and y. But right now, the way I described this, we don't really have that, but we can easily get it. So what I need to do is express this as this boundary as z being a function of x and y. So what is my z? Yeah, just solve this equation for z. 8 minus x minus y. So that is the integrand that we'll use. Okay. So for volume, it's going to be the double integral over this rectangle R that I've drawn here of this function, 8 minus x minus y dA. So this is like a formal method of writing double integrals, but to write this in a way that is actually conducive to evaluating it, we need to fill in the limits that we have. So we'll have a double integral of 8 minus x minus y, and so dy, so our inner integral is dy, and we specify the boundaries for y, 0 to 2. Our outer integral is with respect to x, and we have our limits in x, 1 and 4. Okay, so this is a double integral we're going to evaluate that will give us the volume of this solid. So in this class compared to Cal 2, there's a lot more work involved in setting up the integral you're going to evaluate. This is actually the simplest case right here, because at least your domain is a rectangle. You have constant limits, so there's not really any work in figuring out what your limits are, but there will be in other cases. And that's why, so a very important part of each problem for homework or a test is, do you set up the integral correctly? And then once you've done that, do you evaluate the integral correctly as well? But evaluating the integral is largely Cal 2 stuff. It's just a lot more of it. The setup can be more challenging. So are there any questions about how the integral is set up? So it's your top boundary in z, and the rest of the description of the domain gives you the upper limits for x and y. So now we'll go ahead and evaluate this. Well, I guess I have more room up here. Okay. So 1 to 4, 0 to 2, 8 minus x minus y. All right, so first we're going to focus on this inner integral here with respect to y, and the result of this is going to be a function of only x, which will then integrate with respect to x. So, like with differentiation, we're working with respect to one variable, treating any other variables as constant. So here, we're integrating with respect to y. X is considered a constant. So, if we take the antiderivative with respect to y, what will we get?
8y minus
minus some half y squared.
xy.
xy. Yeah, x is a constant, so you treat it the same way as you treated the 8. Yeah, minus y squared over 2 with limits 0 and 2. Okay, so now we'll go ahead and plug in those limits. So we're going to have, plugging in x equals 2, we're going to get, 8 times 2 would be 16, minus x times 2 minus 2 squared over 2, minus when we plug in x equals 0, well, you can see that we're not going to get anything from that. Okay, dx. So we're going to get 16 minus 2x minus 2. So now we get 14 minus 2x with respect to x. So by evaluating the integral of y is now out of the picture. And now you're back in Cal 2 land. But just for completeness sake, what will we get now?
14x minus what? X squared.
Minus x squared. Okay, with limits x equals 1 and x equals 4. So now we go ahead and fill that in, and we get, so 14 times 4 is 56, minus 4 squared, which is 16, minus 14 minus 1. So our final answer of a volume is 27, and as some students snarkily would write on my test, units cubed, because mathematicians really don't care about units.
Mine's at 27. No, I'm sorry.
Okay, yeah.
I got 50.
All right, but units cubed because this is a volume. All right, so any questions about how this was evaluated? Okay. Now, what I'm going to do is change the example. So still a volume problem, still this integrand, 8 minus x minus y. But the region we're integrating over in terms of x and y is now going to change. So we still have the boundaries z equals 0, x plus y plus z equals 8, ensuring that our integrand is the same. And the rest of our region is specified by y equals x and y equals x squared. And that describes the whole solid, or so three-dimensional region. Okay. So now there's a little more work involved to figuring out the limits. So this is where it's a good idea to visualize what's going on in just x and y. Because with z, we know what's happening. We have our integrand from here, 8 minus x minus y. So if I draw these other boundaries, y equals x, and then y equals x squared is parabola. We can use the intersections of the two to figure out what the limit should be. So, where do these intersections occur? What points are these?
Whenever x is equal.
What?
Whenever.
So 0 and 1. X
Yeah.
equals 0, x equals 1.
Yeah. So so if it's 0, 0 is this intersection, and then 1, 1. So when x and y are both 0 and x and y are both 1, those are the intersection points. So what we can do is use this to determine our limits. So here I've written this as x being the outer integral. The outermost limits, whatever variable they are, the outermost limits must be constant. So if I have my outer integral being with respect to x, I need x values, constant x values, that basically give you the extent of this domain in terms of x. So the leftmost x value you have, because your solid is coming out from the wall. We have this bounding plane out here, x plus y plus z equals 8. And it's everything between this plane and here on top of this region. So the leftmost extent of a domain is x equals 0. The rightmost extent is going to be x equals 1. So those intersections give us the outermost limits. But now, for the y limits, they're no longer going to be constants. The only time you're going to have all constant limits is if you're integrating above a rectangle. And now we're not anymore. So we have to put our bottom boundary down here and our top boundary up here. Our y values as functions of x. So what should I put here and here? So what defines y?
The bottom will be y equals x squared.
X squared, yeah. And this is where visualizing can be important because x squared, but between 0 and 1, x squared is actually less than x. So that's the bottom. And the top?
Will be the one remaining.
Yeah. I know, but okay. All right, x. Okay. So you're always going from left to right when it's x, and then from bottom to top, which is y. Now, if you really wanted to have y be the outer variable, you could do that where you're going from bottom to top in y, and then from left to right in x. So another way it could do this, dx dy. Now, if I want to know what are the bounding y values, those would again be 0 and 1. But now we're going from left to right. So this is also, so y equals x, but you can also think of it as x equals y. So y would be my lower limit, because I'm going from left to right. Now this one goes first, because it has the lesser value. So what should I put up here?
Square root of y.
Square root of y. Because this is y equals x squared, but it's also x equals the square root of y. So if it's easier to express your boundaries as x being a function of y instead of y as a function of x, then this is what you would do. And then your inner integral would be x. So either one will work. Either one will give you the correct volume. We'll go with this one because so that we don't need to deal with pesky square roots. But this has become important later. Sometimes it is necessary to, because by default, most people think, okay, well, dx is our outer integral, outer limits, and then dy is our inner one. But sometimes you need to switch. So any questions about either of these setups?
So like, I guess I'm confused as to why you write on the inner integral, you write x's on the first one, but the y is on the interior.
Oh, wait,
The
this?
y. Yes, that, but in relation to the first, I guess the second interval. I can't remember.
Yeah, so, okay, so what happens is, all right, so when we integrate in respect to x, our limits, they can be constants or they can depend on any other variables other than x. And what's going to happen is, if we evaluate this, the result is going to be a function of y, which we then integrate in respect to y. So you can use whatever order is feasible, and most cases you can go either way with it. But sometimes one is clearly better than the other. So as far as general guidelines, as long as you make sure whichever variable is used in your outer integral, the outermost limits must be constant. And then once you've chosen your outermost variable, when you work your way in, you're now allowed to use outer variables for limits of your inner variables. And so that would be necessary to describe non-rectangular regions such as this. Okay. Any other question? Now when we start to evaluate this, the first step is going to be, the very first step is exactly the same as what happened over here, because we're going to get the same antiderivative, but now we're going to have different limits to plug in, and those limits will be functions of x. And that's what makes things a lot uglier. Okay, let's actually remember to do attendance today. So our volume is integral from 0 to 1 with respect to x. 8 minus x minus y with respect to y with limits x squared and x. Okay, so we go ahead and anti-differentiate with respect to y and get the same thing as before. So 8y minus x y minus y squared over 2, but now with limits x squared and x. Okay. So up top we'll substitute x in for y. So that's going to give us upper limit 8x minus x squared minus x squared over 2. And then we substitute an x squared for y, because on the bottom boundary, y equals x squared. So we have 8x squared minus x cubed minus x to the 4th over 2. So now what we could do is go ahead and condense all this. So here we have 3 terms with an x squared, so we can go ahead and combine those. And we're going to get, and our highest degree term is x to the 4th over 2. We have a cubic term, so x cubed, and then the 3x squared terms give us minus 19 halves x squared. And then finally we have this 8x. Okay. So as we can see, with this integrand compared to the other, we get, back then with constant limits we just had 14 minus 2x. But now we have this. Still perfectly easy to do, even for a Cal 2 student. But then you can just go ahead and use the power rule on this. And in fact, well, I'm going to refer you to page 79 in the notes to arrive at the final answer of 71 over 60, because again, this is something any Cal 2 student should know how to do, even if you're taking the class right now. But the point I want to make with this example is, once you have those limits that can be functions of your other variables, the integrands can explode in complexity, which is a bit unfortunate. But that's why we often have software doing these things. Okay, so questions about this example? I'll try not to make a problem too lengthy to evaluate on a test, but
So, can you explain to me why on this term we're being evaluated from x squared to x instead of x to x squared?
because it's always from bottom to top. When x is between 0 and 1, x squared is less than x. So that's why x squared serves as a lower limit. So it's always from lesser value to greater value. Just as for area under curve, we're integrating over some interval AB, and A is less than B.
Right, I understood that part. It's just like the variables didn't make sense to me.
Okay, so maybe you're asking about a different aspect of it, like.
Yeah.
Okay. Well. Okay, I was wondering. Okay, why is this way instead of the other way around?
No, just the x squared to the x, like y x squared would be less than x.
Oh, because this function is less than this one. For the x values we're considering.
Okay.
Yeah, because if we were integrating between these two functions for x values like over here, further down the x-axis, then x squared would be on top. So what you're always doing.
Yeah, okay, yeah, I see.
Yeah.
Because
It's
it's less than 1.
Yes.
Okay, yeah, I understand.
Okay, yeah, it's always left to right, bottom to top. Okay. Any other questions? All right. Now, another example. Okay. All right. Well, if you're following along the notes, I'm going to jump around a little bit because this is actually my favorite example of the section. Because, as I mentioned with this last example, I set up two different ways. You could evaluate either integral and get the volume, and of course it would be the same volume. But sometimes one order or another is simply not feasible. Okay. So the double integral over region D, but I'll define in a moment, is e to the y cubed. And the region D is defined by, so instead of all points in the xy plane, x is between 0 and 1, and y is between square root of x and 1. Now, this is a kind of description of a domain that's most convenient in terms of inequalities, because then it's obvious which limit is lower and which is upper, because you're always going from lower limit to upper limit. So we can just read off this description to get our limits. So our outer integral is with respect to x going from 0 to 1. And then we have 1 as the upper limit and square root of x as the lower limit. And then we have e to the y cubed dy as the integrand. Okay. Now I'm going to draw this region. Okay, so we have square root of x as our lower boundary, and then our upper boundary is y equals 1. So this is a region over which we're integrating. Now, if we go ahead and try to evaluate this, what you have to do is find an antiderivative for e to the y cubed. And if you have that, then you can plug in the limits 1 and square root of x, get a function of x, and you can go from there. But there's one problem. It is absolutely impossible to anti-differentiate e to the y cubed. All right, all the techniques that you learned in Cal 2, and even techniques out there that you didn't learn there, and there are quite a few more sophisticated ones, would not help you get this. So e to the y, very easy to do. That's just e to the y. But e to the y squared, e to the y cubed. I talked about e to the y cubed, y squared. It was actually e to the minus x squared, very first day of class. So the only thing you can do with functions like these is try to approximate the integrals. And you may have learned about these techniques in Cal 2 if your instructor covered them, like trapezoidal rule, Simpson's rule, etc. But here, with this double integral, we have another option. So we don't have to settle for approximating this, and now's not the time to talk about those anyway. We could change the order of integration. So have x as our inner integral and y as our outer integral, and work it out that way. And so then we have to figure out what the limit should be. So what we'll have is same integrands and dx for our inner integral and dy for outer. But now we have to figure out the new limits, and this is why I drew the picture. Because if I was just going to go ahead and evaluate this based on these inequalities, I wouldn't need this picture. I have the limits. But since I'm about to make a change, the picture can be helpful, just to make sure you don't get things backwards. So if my outer limits are going to be y, I need to know what is the extent of this domain, like what is the bounding y values. So what should my what y values define the extent of this whole domain that I've shaded here? Like what's the smallest y value that I have?
0.
0, because of this tip right here. So the domain never goes below y equals 0. So, and then up to 1.
1.
Yeah. Okay. That's pretty easy. Now, so from bottom to top, y going from 0 to 1. Okay. Now, for x, I'm going from left to right. So lower limit is?
0.
Yeah, because of this boundary right here. And then, what about the so the rightmost x value?
1.
But you have to account for this curve,
Y squared.
not y squared. Oh, sorry. You're absolutely right. It is y squared. Sorry, I started on Monday. Yeah, because y equals square root of x, if you write it x as a function of y, you have x equals y squared. Okay. Anyhow, so now, well, first any questions about the setup?
Why can't you just say that y squared is equal to x is equal to 1?
I didn't have 1 up here,
Right.
because then you're integrating over a rectangle. Because, here's one way to look at it. The question you're asking for the inner limits is, because now I'm set on y going from 0 to 1. For each y, what are the x values you need? Now, when y is equal to 1, yeah, you want x to go from 0 to 1. But for y down here, like around 1/2, you only want to go from here to here.
I see.
Yeah.
Thank you.
Well, since we switched dx and dy, how come we didn't switch the intervals?
Well, these are the limits in y, and these are the limits in x. Whereas before, it was the other way around. These are limits in x, these are limits in y.
So how come our limit for y isn't the square root of x to 1 and y is at 0?
Because here, because before we had our boundaries defined y as a function of x.
I see it.
And we need x as a function of y.
I see.
Okay. You have a question? Now, since we had a possible integrand before, how is this changing order going to change things? Because now, instead of integrating e to y cubed with respect to y, we're integrating it with respect to x. So e to the y cubed, as far as we're concerned, at this moment, is a constant. So when we carry out the anti-differentiation with respect to x, what are we going to get?
E to the y to the third x.
Yeah, so we just multiply by x. and we fill the limits 0 and y squared. And now we plug in y squared for x and also 0 for x, which isn't going to give us anything. So now we have the integral from 0 to 1 of y squared e to the y cubed dy. Now, whereas just integrating e to the y cubed was impossible, why is it that this one is now possible? What would you do?
U substitution.
It's a u substitution. So we let u equal to y cubed. So then du is 3y squared dy. So once you account for the substitution here, so y squared dy gets absorbed into 1/3 du. So we get 1/3, and now we're just integrating e to the u du. And if you plug in the limits 0 and 1 into the substitution, you're still going to get 0 and 1. So now this is your integral. And now you go ahead and evaluate that, and you're just going to get e to the u. So you get 1/3 e minus 1. Okay. Any questions about that one? Okay. Now, okay, there are certain properties of integrals that I need to cover, and then we might have chewed up our time by then. All right, and it looks like we're doing pretty well time-wise, so on Friday we'll have time for homework questions, so be sure to bring them. I know some of these properties of double integrals are ones you would recognize as also applying to single integrals, but it's important to keep them in mind. Okay. So first we have what's referred to as linearity. And this is one that we've used already. So if you have the double integral over some region of a sum of functions, then you can just pull them apart, evaluate two separate integrals. Okay. And it's something that you did routinely with single integrals. Here's another that you'd be familiar with, and it's called homogeneity. So if you have a constant times a function, you can always pull out the constant, which you were accustomed to doing in Cal 2. But there's one special case of this that wasn't really an issue in Cal 2, but can be used often when evaluating multiple integrals, double integrals, and later we'll get to triple integrals. And it's really a consequence of this. Suppose you are integrating over a rectangle, so you have constant limits for all variables, and your integrand happens to be a function of x times a function of y. in that case, you can, so for instance, what you can do is you can take this f of x, because it doesn't depend on y, and pull it out to here. But at the same time, as far as x is concerned, this integral of g of y is also a constant, so you can pull things out that way too. So by applying this property twice, what you can do is break this down to a product of two single integrals. So integral a to b of f of x times integral from c to d of g of y. And especially when we get to other coordinate systems, like dealing with polar coordinates, spherical coordinates, it'll happen quite often that we can take advantage of this. So at least you may have many integrals running around, but each one will be simpler to handle. So it kind of reduces the clutter. Okay. This next one is important for the fact that very often geometric meanings to integrals, areas, volumes, and so forth.
We have to keep our constant, don't we?
What?
We have to keep the constant. We still multiply by the constant when we're done.
Well, yeah, you still multiply these together.
And then by the constant.
Well, I don't. In this particular case, I don't have a. Are you just referring to this, or yeah, you still multiply that at the end. Yeah. Yeah. So this is just another application of this property. Just because if you're integrating with respect to one variable, all other variables are treated like constants. All right, the next property, referred to as monotonicity, is if your integrand is non-negative on your domain R, then the integral over R also has to be non-negative. In fact, when this happens, unless f is equal to 0 throughout the domain R, your integral will actually be strictly greater than 0, because if you're never going to go below the xy plane, there's no possibility for a negative contribution. So this would be important for problems where you know it's a volume problem. You should definitely not get a negative answer for that. And then we have additivity. So if you have two regions whose union makes up a third region, then you can also break up your integral over the larger region into a sum of that same integrand over those two subregions. And as we get into vector calculus, we'll take advantage of that. But sometimes if you get some unusual shapes, for instance, maybe you have an L-shaped domain like this. Well, it'd be very cumbersome to describe limits for x and y to describe the entire domain. But if you break it up right here, so this is your R1, this is your R2, then you have two rectangles to work with, so it's the simplest possible case. So you can just handle each of these and add them together. And finally, I just have a couple more, so don't back up yet. All right, so we have if your function, your integrand is bounded by certain values for x and y in some domain D, like a rectangle, then the integral is bounded by capital M times this. This is the area of D. I'll be using this abbreviation on other occasions. And greater or equal to little m times the area of D. And finally, last thing I swear, mean value theorem for integrals. You may remember mean value theorem for derivatives in Calculus 1, that the integral, the double integral, is equal to the value of the function at some unknown point within your domain D times the area of D if f is continuous on D. And that can be very helpful, especially if you're able to determine how small or big this can be. It can help with estimating the values of integrals, which is very important in other areas of mathematics beyond Calculus 4. Like in numerical analysis, this kind of result is used all the time. Okay, I'm done. So we'll have a little more to do with integrals on Friday, but go ahead and bring home more questions too.